For the translational equations of motion, we have the sum of the forces in the up or the y direction is equal to the combined force of lift due to the central rotors minus the gravitational force due to the mass of the helicopter is equal to that mass times the total acceleration in the y direction. In order for the helicopter to rise, the force of lift has to be larger than the gravitational force, which can be done by increasing the thrust on the controller. And then in order for it to fall or go down, the forces of the lift must be smaller than the force of gravity, or decrease the thrust. The rotational equation of motion is the sum of the torques is equal to the torque from blade set 2 minus the torque from blade set 1 minus the torque of the tail is equal to the equation for torques about the center of gravity or mass that we derived in class. As you can see, in order to yaw, the torque of one blade set will be increased to more than the magnitude of the torque from the other blade set, since the two sets of blades are counter-rotating. In order to pitch, a torque is added to the tail blade. For general motion, the tail blade does not produce a torque in order to simply rotate or move up and down. However, the torque is necessary if you would like to translate forward or backwards. If a torque is added to the tail blades, then the translational equations of motion change. When a torque is added to these tail blades, it causes the helicopter to pitch. If the thrust of the counter-rotating blades is kept the same, this will cause translational motion in the forward or backward direction of the helicopter. In the free body diagram pictured, the helicopter will move backwards. We can see this because the forces of lift have a component in the x direction as well as the y direction. We can see that the sum of the forces has become a more general equation and is not purely in the y direction. With the addition of this pitch due to the torque from the tail blades, the coordinate frame of the body will change. Normally, the counter-rotating blades stabilize the helicopter and prevent it from pitching and rolling. With the addition of a tail blade torque, the helicopter pitches and the body frame rotates, which means that the up direction for the helicopter is no longer the same as the up direction of the ENU coordinate frame.
What is shown here is the block diagram for the helicopter dynamic system. The first step of the system is the inputs. In this case, the inputs are given by the pilot of the helicopter and sent to the PID controller. The PID controller then inputs the data into the helicopter dynamics. These functions output into the measurements. The measurements take in the torques and translational motion and calculate the Euler angles and Euler rates. These angles and rates get put back into the PID controller as feedback for the system. From here, the PID controller takes into account the pilot's desired outcome as well as the current state of the helicopter and calculates an error value as the difference between the measured process variable and desired set point. The helicopter dynamics adjust and output the pilot's desired flight path.